Hello everyone, welcome back to the Computer Network course. Right now we are still in the network layer control plane chapter, and this time we're going to learn a bit about introduction to the software defined networking or SDN control plane. But before we talk more about SDN, I just want to give you some little background information. So did you know that in the previous editions of the Computer Networks book by Ross, which is our textbook, network layer was only presented in a single chapter, but in the 7th edition or in the current edition of this book, the explanation about the network layer is divided into 2 chapters, which is data plane and control planes. So why this is so? This is because the new approach introduced by the SDN, which divides the data plane and control plane into different locations. So we'll talk more about this SDN in a moment. So previously, when we talk about the various routing algorithms and protocols, our basic assumption was that the routing capability is embedded and distributed in every single physical router. In other words, the control plane functions, including routing calculation and decisions, together with data plane functions, happens in the physical router. So this is what we call the per router control plane or monolithic approach. And by the way, this approach is still implemented in the legacy system, legacy routers, even until now. And also, secondly, in the per router control plane, we used to have different middle boxes that implements different functions such as firewalls, load balancers, and so on. But then in around 2005, some researchers from Stanford University started a Nathan project that later became OpenFlow project, which is an open source SDN platform, which becomes like it marks this the beginning of the rethinking of network control planes, right? So let's recall this figure on the per router control plane. As we can see that the control plane and data plane in the per router control plane are located in the one single routers, right? But then in the logically centralized control plane, which is applied by the SDN, the control plane functions such as the routings and packet filtering and so on are implemented in the remote controller. And then the results of these functions, for example, like flow table as a result of the routing computations, and then other relevant information are going to then sent to the data plane switches through a component called the CA or control agents. Okay, so it is also important to note that although it is called centralized control plane, but doesn't mean that there is only one central controller used. In reality, the controller can be deployed into multiple servers within one or more data centers. Alright, so why a logically centralized control plane? First of all, it is easier in network management, such as we want to avoid router misconfigurations because we don't have to configure each and every single router individually. And also we have more flexibility in managing or engineering our traffic flows. And we'll talk about more about this traffic engineering or traffic flows in a moment. And secondly, we can use table-based forwarding, which allows the programming routers through the remote controllers. So, for example, in the previous discussion about link state algorithms, if we use per router control planes, we need the link state algorithms need a topology map. Okay, so this topology map can be created by sending broadcast message from each of the node in the networks. So this, as a result, there will be a lot of message exchange going on in the network, or message broadcast in networks from each of the nodes. If let's say we have a lot of nodes, then there will be a lot of message broadcasted to all the nodes. But in let's say in a logically centralized control plane, all the nodes in or like the data plane switches simply need to send information about the neighboring cost to its neighboring routers to the central controller. So it is much simpler than having broadcast messages going around in the networks. Okay, then this computation will be done in the controller, and then the controller will distribute the flow table computation to the data plane switches. Alright, and then lastly, there is open and non-proprietary implementation of control plane, which is more preferable than proprietary control plane implementation or specific to any routers or vendors. Right. Okay, so I'm not going to explain the details of these slides. I think it's quite clear. We can make analogy between router control plane and logically centralized control plane with the mainframe to PC evolutions. Okay, we'll skip these slides. Okay, so let's talk about the traffic engineering, or the issue in the traffic flow engineering when we use the classical approach or per router approach. Oops. So let's say if we want to engineer our traffic or route the traffic from U to Z through U, for example, U and then V, W, Z, what we can do is that we have to change the weight or link cost, right? Because if we use, let's say, the existing routing algorithms such as link state or distance factor, most probably the path that will be chosen is from U, X, Y, and then Z, because this is the path with the least cost. So, first, changing the link cost is not possible because the link cost is something that is given by real networks. On the other solution is that we have to find new routing algorithms. So, and then the second case is let's say we want to load balance the traffic from U. So traffic will go through U, V, W, Z, and the other one is from U, X, Y, and Z. Again, this is not possible to do because we cannot modify the link weights, or we have to create new routing algorithms. And lastly, let's say we want to have different flow of traffic coming to router W. Again, it is not possible to do with the existing routing algorithms with per router control planes. But with the logically centralized control plane, we can easily, or we have more flexibility to, let's say, engineer our traffic flows within networks. All right. This doesn't mean that we cannot implement link state, let's say, link state routing algorithms in the SDN or in the logically centralized controller control planes, but we can have more flexibility in engineering our traffic flows. So this is the general overview of SDN components. First, we have data plane switches in the data planes, and then we have control data plane separation, and then we have the SDN controllers. All right. And then lastly, we have the network control apps. Now let's take a look at each of the SDN components in more details. First, in data plane consists of several SDN control switches or data plane switches. Data plane switches is in principle fast, simple commutative switches implementing generalized data plane forwarding, which we have discussed in section 4.4. And what it means is that we can just obtain, let's say, generic switch, okay, and programmable switch, and we don't need to, let's say, use any specific router with specific functionalities, because the main functions, for instance, the routing computation is computed by the central controller, and the result of this computation is the flow table will be sent to the or distributed to the data plane switches by the controller. So it also has API for table-based switch control and a protocol for communicating with the controller. Alright, so in the control plane, we have two components, SDN controller and the network control applications. So that SDN controller is also called as the network OS, operating system. It maintains many network state information such as the link state information, the flow tables, information about the switches, statistics, and so on. And it also interacts with the network control applications above, like it's above via northbound API, and it also interacts with the network switches below via southbound API. Right. Network control apps is essentially the brains of the controller. It implements control functions provided by the SDN and also through the API provided by the SDN controller. And since the API is open, so basically the applications can be implemented or developed by any third party, irrespective of let's say any vendors used or any SDN controller implementation that is used. So now let's take a look deeper into the SDN controller. So the SDN controller can be divided into three important layers. The top layer is the interface layer that provides abstraction API to network control apps above. And then in the second layer is the network-wide state management layer, which provides all the important information about the networks, link state information, host information, switch information, flow tables, and statistics, and more. And then in the bottom part, there is communication layer, which provides communication between the SDN controller and the data plane switches. Then there is open flow protocol, which is responsible for the communication between the data plane switches and the SDN controller. So it uses TCP to message exchange and with optional encryption. There are three classes of open flow messages: controller to switch messages, asynchronous or switch to control messages, and symmetric messages. But at this time, we'll only talk about the control to switch messages and switch to controller messages. So there are several controller to switch messages, and some of them are features message, where the controller queries switch features, and then the switch will reply with its available features. And there is configure message, where the controller queries switch configuring parameters, and then the switch will reply with the parameters that it has. Or the controller can also set specific parameters to the switch. And then there is modify state message, which add, delete, or modify flow in the open flow tables, which is already installed in the data plane switches. And there is packet out message, where the controller can send packet to specific switch port. And then we also have several switch to controller messages, and some of them are first a packet in message, which is related to the packet out message, where the switch can send packet back to the controller. And then there's a flow remove message, where the flow table entry deleted at the switch. So if there is any removed or deleted flow table entry in the switch, it will be sent to the controller. And then there's port status message, which informs the controller if there is any change on the port, such as for example, if there is any link failure in the in one port of the switch, then it will send this information to the controller. Cool. So although this message is originated from the switch to controller, but we don't have to set, or we have to program the message directly from the switch to controller, but instead we can use higher level abstraction at the controller to control this message. So let's have a look at the example of control plane data and data plane interaction in the SDN. So for example, the S1 or switch 1 is experiencing a link failure between its link with S2, switch 2. So it will immediately send open flow message called port status message to notify this failure to the controller. And then when the SDN controller receives the open flow message, it will update link state information. So link state information can be it's actually similar to the link state advertisements in the let's say link state algorithms in the per router control planes. And then this change in link state information will trigger or will call the Dijkstra link state routing applications outside of the controller. So the Dijkstra link state routing application needs information from network graphs and the link state information. Network graphs is also similar to the topology map that we use in the link state routing algorithms. So based on this information from network graphs and link state information, Dijkstra link state routing will compute new routes based on the available information. And then after computing the new routes, the link state routing application will update the flow tables in the controller, and then the new flow tables in the controller will be distributed and installed to the all relevant network switches or the data plane switches. So alright, so that's example of the interaction between control plane and data plane in the SDN. So there are several implementation of SDN controllers, but I'm not going to explain in details of both examples. We have Open Daylight or ODL controller and ONOS. I just want to give you one major difference between these two. In ODL, network apps may be contained within, or so it can be within the controller, or it can be also outside of the controller. But in ONOS controller, the control apps is separate from the controller, so it's outside of the controller itself. So finally, we'll just a little bit on the key challenges in the SDN. The first challenge is related to the security challenge, especially in the availability aspect. Here, the hardening refers to terminology in the security where we want to limit or minimize the access to a server. So, for example, if we don't use any SMTP service in our server, so we have to close port number 25, and if we don't use any HTTP or HTTPS services in our server, so we have to close port 80 and port 43 because these open ports can be let's say a whole security hole for our system that can let the intruder to enter our system. And also, even if we, let's say, we use SSH services to configure our server remotely, we should limit the access, for example, from specific IP addresses or from specific subnets. So that's about the hardening. And then the dependable, reliable, performance scalable, these are related to the robustness to failures or related to the fault tolerant systems, where the system should be able to continue to operate even though there is failures in one of the components. So normally this is done by implementing redundant systems, right? And then the second challenges related to the network and protocols of the SDN and how they meet the mission specific requirements. So for example, if we take this example from this interaction, one of the requirements would be the real-time requirements. How fast we can install or we can generate new flow tables if we experiencing link failures in the switch. So this will define whether we can meet the machine specific requirements. And then the last challenge is about internet scaling. So internet scaling is related to deploying more networking devices, especially routers and switches. And this challenge is that we need to ensure the scalability of the controller when we increase the data plane switches more and more. So, so basically this is all about the SDN. It is just an introduction of the SDN. If you want to gain more knowledge or practical experience on the SDN, you can try to attend Advanced Computer Networks course in the Magister of Computer Science program, or you can check any open course or tutorial on the SDN. So I think that's it for now. See you again in the next video. Bye.